So how can you do that? So to do this, we have the Simulink test, which allows you to create tests based on your model. So you need to create the tests manually from the high-level requirements. You create tests manually where you define the inputs that could be defined either in an Excel file or in a math file, could be used in the signal editor. You could use a test sequence when you describe your test with some sequences. I first change speed, then I change the speed of the engine, then I change the pressure, and then I measure the output and I verify that the output is at that level. That could be done on sequences. You could use MATLAB code or you use the state flow. But the important thing here is that from the requirements, you define the inputs and you define the expected outputs. You need both. And if your requirements are, your high-level requirements are complete, consistent, accurate, unitary, you should be able to do that. If you're not able to create tests with inputs and outputs from the requirements, from the high-level requirements, it means that you need to review your high-level requirements. So once you have the inputs and expected output, this can be done by someone that doesn't know the model. This is done using the high-level requirements. So the person that is developing the model use the requirements, and the person developing the test could be someone independent who doesn't know how the model is done, but he knows that with these requirements, if I have this type of inputs, I will get this type of outputs. So with the inputs and the outputs and Simulink test, then you can manage several tests and trace these tests to the requirements, and then run all the tests. And what Simulink test does is that it verifies that the output of Simulink is the same, the output that you defined. And in Simulink test, you define the output either, again, with some Excel file or some MATLAB file, meaning that it will compare output of Simulink and the output of these files. You can add some tolerances, for example, on the relative or absolute tolerances, and could be also tolerances on time, depending on when the value is achieved. Or you can use the assessments. In the assessment, you can do, once I've got this sequence here, I want to verify that I get this value. And then once you launch a Simulink test with all of your tests, you can also collect the coverage of your model. And this uses Simulink coverage. And Simulink coverage will tell you, once you run all the tests, so you need to have a pass for all the tests. If it fails, it means that either you need to fix a problem in the design model, or you need to fix your test, and maybe your test is wrong. But once everything is passed, then you can look at the coverage and see if you've got everything that is covered. So what you are looking here is to get 100% coverage, meaning that all the tests were able to cover any element of your model, which means any low-level requirements. And in that way, you show that your low-level requirements are verifiable because you get 100%. If you don't get 100%, you will have, in the report, it will tell you which part of the model is not covered by your tests. You will see on the report, and you can see with coloring code on your model as well. So here we can see that this transition for Gear 2 to Gear 1 was not covered. So it means that I'm lacking a test for that. And once I have that, I need to either create a new test to pass this one, because obviously here something is missing. Or it could be that I don't have a requirement for this one, so I didn't put the test. Or the person who creates the test but didn't put the test because the requirement was not there. So we need to create a new requirement, high-level requirement, and then provide the associated test. Or it could be that this part is never reachable, it's not possible, and then I need to explain why. It could be that it's because I'm using a component from another project, but in my new project, this part will never be done because I got some configuration, so I need to justify it. Or this is a bug, and I need to correct the design. So now we've done some verification at the design phase, using a Simulink state flow for the architecture, Simulink design, Simulink check to verify some modeling guidelines, the requirement toolbox to do the traceability between the requirements and the model. Simulink report generator allows you to customize some reports, and Simulink test to simulate the model against the high-level requirements and give you a status pass-failed, and Simulink coverage to show the coverage of your model and to say that all the elements of the model are verified. Now let's look at the source and integration phase. From the model, you will, from the level requirement / model, you need to create the source code, and this is done by embedded coder. To answer table A2, source code is developed, and you don't need to be specific. You don't need to provide the files when you do level D. Embedded coder is the code generation tool that can produce C++ from Simulink models, and the objective of this tool is produce code that is fast, efficient, readable, traceable, deterministic, meaning that you can certify this code. You see, when you generate the code, you can put in regard the generic code in regard of the model, and you can see the traceability. For example, when I click on blocks, I can see the parts of the code highlighted representing this part of the model. The opposite is also true. You can click on one of the line of code, and it will highlight the blocks that correspond to this line of code. So here we can see the line 56, where phi is bigger than 6 or less than -6, which is represented by these blocks, where we can see phi is bigger than 6 or less than -6. We've got the or here, and we've got the if this block is true, we'll pass phi. If it's not, we pass 0. So the code is, you can add some comments. Comments can come from blocks, and in the blocks you can have in the description, you can add your own model, own comments that will appear on the code. On the source code, now there's an objective to demonstrate that the source code complies with coding standard. This is table A5, source code conforms with standard, and which is the required for level A, B, and C. This can be done with Polyspace Bug Finder. Polyspace Bug Finder allows you to analyze any type of C++ code. It can be used with code coming from Simulink, but it can be used also for the code done manually. Remember, and some parts of the code are written manually for the drivers, for the task, etc. So you can use a Polyspace Bug Finder for both, and for both you need to demonstrate that the code complies with the standard, and you can decide that the standard could be MISRA C 2023 or 2012. There's also 2004 that is supported. You choose it. DO doesn't say what standard you need to apply. It's like for the model. You decide, you define your own standard. Then you need to show that the source code is traceable and is compliant with the model. This is done with a tool that is called Simulink Code Inspector, and this answers the objective 1, 2, and 5 of table A5. And you see here that for source complies with low-level requirements and source code complies with architecture, this must be done with independence. And this is why the Simulink Code Inspector is developed also with independence, and we've got some artifacts to show you that they develop from independence with embedded coder. So how does Simulink Code Inspector works? It takes as input the Simulink model. It takes as input the C code generated by embedded coder. Then it does intermediate representation for the model and for the code. It normalizes this representation and tries to match all the nodes, each of the representation. If there is a match, we've got a traceability and a conformity. If something doesn't match, then there is a failed to say that, okay, there's no matching between the model and the source code. So at the end, you will have a report which gives you the traceability with all the lines of codes and the models, and the conformity with all the blocks that were analyzed by a code inspector. Then once you've got your source code, you generate the object code. You need some compilers that are provided by your microcontroller that you are using. If you're DAL A, if you remember, there's 69 objectives in B and 71 in A. There's 2 objectives more in DAL A. You've got MCDC, plus you need to demonstrate the traceability between object code and source code. And this, we don't provide any tools. This usually is done with a sample of object code, and this is done manually. But here, what we can do with the tools is verify the object code against the low-level requirement, and we can use here Simulink test and coverage again, and Simulink and the Polyspace code prover. So here we're now answering some objectives of table A6. Object code is robust with high-level requirements and is robust with low-level requirements. This can be done using Polyspace code prover. This tool is used for C++ code, like Bug Finder. It can come from embedded coder, or it can come from your manual code. again, can be used for the code of the drivers, the task schedulers, etc. And when you run Polyspace Code Prover, it gives you a coloring mapping on your code to say when it's green, it means that there's no fault on this variable. When it's red, it means here there's a fault, you need to correct it. When it's gray, it means that you've got dead code. And when it's orange, it doesn't prove anything. So you need to review it manually. And so Code Prover is capable of finding 30 types of runtime errors like division by zeros, overflow, pointer non-initialized, out-of-bind arrays. So 30 defects that would lead to a runtime error and the crash of your processor. Most of these runtime errors are explicitly cited in the DO to do robustness testing. And if you use Polyspace Code Prover, you don't need to do this robustness testing for those types of errors. You can prove it directly with the tool. And finally, showing the object code complies with high-level requirements. So here we've got table A6, and this can be done using Simulink with a Simulink test. And instead of running the model itself, you run the code generated from the model that you can run on the target. Meaning that you use the Simulink test environment, and in the Simulink test environment, you say, run the model in normal mode, which is model coverage, or you say run the model in processor in the loop, meaning that the code from the model is generated and downloaded into your target. And then Simulink test sends the inputs coming test defined in Simulink test to the target that runs one step and provides the result to Simulink test that can say, I can compare it now with my expected output and do a pass or fail. And doing so, it allows you also to find out the number of cycles that were used for each of the functions and gives you an estimate of time. And so this helps you also to do the worst case execution analysis that is also needed is one of the objectives of the DO. So you get this kind of reports for each of the function. It tells you what is the time for each of the function. And then you can do further analysis to find out if it fits the task allocated to this, the time allocated to this task or not. And you may need to change your design for that. In table A7, we've got all the structure coverage. You need to show for ABC that the tests that you provide were covering the statements, the decision, and the MCDC. Again, Simulink coverage allows you to do that. So remember, with Simulink test, you create your test with input expected outputs, and you can couple it with Simulink coverage. When you run it at the model level, you get model coverage. When you run it in processor in the loop, like I just explained, you get the coverage of the code. So that allows you to answer the objectives of table A7 that I just described. We've just seen the tools used for the coding phase. So embedded coder to generate the code automatically. Simulink code inspector to verify that the code and the model are traceable and comply one with each other. Simulink test, where you use the same environment, you don't have to create new test cases and you use the same that you used at the model level. This time you just configure the model either running the code in software in the loop in your PC or processor in the loop, running it in the real hardware. And with Simulink test, you perform the simulation and you get a pass-fail. Simulink coverage applied in software in the loop of processor in the loop give you the code coverage. You get the report with the statement, decision, and MCDC. Polyspace Bug Finder allows you to verify that the source code complies with coding standard. Again, source code coming from Simulink or produced manually. And Polyspace Code Prover allows you to prove that the source code is robust against 30 runtime errors. So you don't need to provide extra tests to demonstrate that your source code is robust to these runtime errors. You can prove it formally with Polyspace. So we've seen a lot of tools here, and when you are using tools in DO, you may need to qualify them. And there's a chapter in DO-178C describing the tool qualification, and there's a document, the DO-331, that explains how to qualify the tools. So when do you need to qualify a tool? So this comes from the DO-178C. When, if I read, the qualification of the tool is needed when processes of this document, so the DO-178C, are eliminated, reduced, or automated by the use of a software tool without its output being verified. And the purpose of the tool qualification process is to ensure that the tool provides confidence at least equivalent to that of the processes eliminated, reduced, or automated. So it means that if I'm using a tool, but I'm reviewing the output of the tool, I don't need to qualify the tool. Most obvious example here is Simulink. I'm using Simulink to create the low-level requirement, but then I do the analysis on the Simulink model to do the traceability with the low-level requirements. I will verify with some simulation. So I do verify the output of Simulink, so I don't need to qualify Simulink. Another example is embedded coder. From Simulink, I generate embedded coder, but then embedded coder generates source code, but then I verify the source code. I verify the source code complies with a coding standard, with policy-based bug finder, and I verify that there is traceability between source code and the model, and I verify the conformity between source code and the model with Simulink code inspector. So I don't need to qualify embedded coder. But then I need to qualify policy-based bug finder and need to qualify Simulink code inspector because I don't verify their output. So to do the qualification, DO says we need to classify the tools that you're using. And DO defined 3 criteria. Criteria 1 is a tool that could insert an error in the final product. Criteria 2 that does not introduce an error in the final product, but could fail to detect an error. And the end is important here, are used to eliminate or reduce other verification process or development processes. For example, the only tool that we have that is criteria 2 is policy-based code prover, because you are using policy-based code prover to show that the source code does not produce runtime error, and then you eliminate other verification process, which is, or reduce the robustness testing, because you don't have to produce the test to verify that your code is robust against division by 0, for example. And the last criteria, which is all MathWorks tools are criteria 3, tools that could fail to detect an error. For example, when I'm using a Simulink check to verify that the low-level requirement comply with the standard, the tool could fail to verify that I'm not complying with one standard, one rule. I'm not injecting a default in the model, and default was already there, but then it fails to detect it. So this is the purpose of this criteria 3. And depending on these criteria, you will need to qualify the tools with different level. With the level 1, which is with most activities, and level 5, less activities. And you see that for criteria 3, whatever the DAL, tools must be qualified with the level 5. And here for criteria 2, tools must be qualified to level 4, DAL A and B. And again, only code prover falls into this category of criteria 3. Okay, so what does it mean qualifying to TQL 4, 5, or 1 or 2? At TQL 5, you need to provide to the authorities a tool operational requirement. What is that? Is a document where you describe all the features of the tool, what the tool is doing. For example, for Simulink check, the tool is verifying that all the inputs have a data type specified, all the inputs have a dimension that is specified. So you describe what the tool does, that's the rule, and Simulink check verifies that all the inputs have the data type and dimension specified. If they are not specified, it raises an error. So tool operational requirements describes what the tool does, and then you need to provide a tool operational verification and validation case and procedure, meaning that for each of the requirements that you have in the tool operational requirement, you need to have a test. In my example of Simulink check, with the rule that all input ports must have the data type and dimension, you have a test case where I've got a model with the input ports where I do have specified data type and dimension, and I have a second model where I don't specify the inputs and dimensions, and I have a test case which runs the first model where the report says passed for the rule, and when another test that runs the check for the second model, and with the result failed. So this is what you need to do for each of the tools that you are using where you don't verify the output. And this is true for your own tools. If you create your own tools that eliminates or reduce an activities that has bad DO and you don't verify the output of your tool, you need to qualify them and you need to provide this tool operational and the test case and procedure. At TQL4, you need to go a step further where you need to describe how the tools are done. And you need to provide also a tool qualification plan. And so this means that you need to know how the tool is done. So usually you need the help of the editor. This is where we provide also this information. And for TQL3, 2, and 1, you also need to define the tool development plan, you need to define the tool verification plan, you need to define configuration plans. You follow basically all the activities of the DO. So this is why it's very costly to qualify tools criteria 1, because you have lots of things to do. So we do provide to help you qualify the tools. I didn't mention it, but tools are always qualified by the user. It's never the editor who qualifies the tool, because the user is using the tool in one configuration. It could be a Windows, it could be a Linux, and you need to qualify in your environment. I don't know which version of Windows you're using, which version of Linux you're using, but you will need to qualify the tools on the environment, use the tools. And so for TQL4, you could qualify the tools without our help, but to help you in this qualification, we do provide a qualification kit where we provide the tool operational requirements for each of the tools, where we define all the use cases. We do provide the tool qualification plan also. Also, it is not needed for TQL5. We include it because it's something that you can then use directly in your PSAC. And in this tool qualification plan, we describe the criteria, we describe the objectives that you can eliminate with the tools. And of course, we also provide, and this is what takes most time, we provide the test case and procedures in regards to the features that we specified in the tool operational requirements. So for you to qualify our tools, you will need the tool operational requirements to find out which are the features that you are using, probably all of them. Maybe for the Simulink check, you will decide, I will use this feature for this rules, but not this one because I don't use a rule. And then you need to run for each of the environments that you are using for development, you will need to run the test case and procedure. Let's say that you've got a Linux environment, you will need to run test case in Linux. And you've got another environment in Windows, you also will need to run the test case procedure in Windows environment. And then you need to verify that the output of test case and procedure is the same as the one that we provide in the tool qualification kit. So here are the tools that we provide the artifacts for qualification. So the Simulink report generator, the Simulink comparison, the Simulink check, Simulink design verifier, the Simulink requirement, Simulink test, Simulink coverage for the coverage of the model and the code, Simulink code inspector, Simulink code prover, and the bug finder for the MISRA rules. So we've seen there's a lot of things to do in DO in general. If you are using models, we see that we can automate some objectives like the review of the standards for the low-level requirements, traceability between requirements and high-level requirements, compliance with high-level requirements with the simulation. So there's lots of things that are automated because you are using a model. If you're not using a model for the manual code, then you need to do these reviews manually with lots of time doing analysis between the text and the high-level requirements or the source code. So to help you put in place this workflow with the model, we provide you some support with some training. We do have trainings on the tools like Simulink, obviously, to create the architecture, but also on code generation and also on verification using Simulink test, Simulink coverage, Simulink check. And we do recommend also consulting to help you assess your existing workflow. You probably already have a manual code workflow, and we can assess it to see how we can derive it, define and optimize it for an MBD workflow. Consulting can also help you to configure and customize some tools. Let's say that for Simulink check, you want to use some of your tools. We can help you create your own tools. Also, we can help you qualify checks that you added, and we can also support you with audit with the authorities once you've got a process in place. And so the recommended support is really working in combination with the training. So coaching with the planning phase, then training to train all the people on using Simulink, doing the architecture, creating some project, linking that with configuration management, and then the consulting to help you put that in place, all the parameters, all the how to divide your project in several modules, how to link it with GitLab, for example. Then some training about code verification, about Simulink test, check, coverage, and with the coaching to help you create your first tests, and then you can create all the tests. And then training about code generation. Code generation is a 3-day training, is very dense one. So I strongly recommend training plus consulting so that our engineers can help you tune the code generation to your need, because obviously you will produce code for the application that will need to be integrating in manual code. So then the purpose is to generate the code that fits exactly into your manual code. And I would like also to recommend to automate. So if possible, use a continuous integration where you automate all the activities of testing, checking, analyzing, so that when you got new modification on the file, you push it and automatically it generates the code, it launches Model Advisor, it launches the test, it launches PostSpace, and then it publishes the results, and then you review the results. Okay, just at the end of the presentation, so as a conclusion, what I present should help you get certification credits using model-based design. Will get you credits for model-based design. And I would recommend 5 things here. First, when you write the requirements, the high-level requirements, have in mind how I'm going to test the requirement. If you do that, it will ease the work of the testers, and it will provide requirements of better quality. When you create the design model, use reference models and data dictionaries, so that the model reference decrease the complexity of your model and enforce the data types, so you can detect rapidly if there is an error on the data types, and use data dictionaries and with several dictionaries for each of the components, so that you can also get the dictionaries in configuration management and see the evolution of the data in the dictionary. Work with the quality assurance team to explain them what you're going to do with the model, because usually they don't know the models, they know textual, but explain them what a model is. It represents a low-level requirements and the credits that you're going to do and verifications that you are going to do. Meet with the certification authorities very early at the planning stage to agree with them about all the credits that you are going to take from each of the tools. And so at the planning phase is the right time to validate them with them, because if they don't agree, then you can change your way of working. And the last one is automate as much as possible using continuous integration. Where we see, so models address DO-178, DO-331. We do provide a qualifications kit to help you with the qualification, and we can help you through training and consulting. So that's the end of my presentation.